Lab 1 charge tape for Physics 2212. So the agenda is the introduction, models, our experiment, our code, discussions, and conclusions. The purpose of this lab is to use experimentation in order to approximate the amount of excess charge on a piece of charge clear tape. The principles and models that we use are Coulomb's law, which describes the force between two charges, so that's force equals Coulomb's constant times the charges of both charges divided by distance squared, or magnitude of r squared times r hat. We also are going to use Newton's second law, which is force equals mass times acceleration, and this describes, and then we're also going to use the momentum principle, which describes the change in momentum is proportional to net force. We're also going to use gravitational force, which is the attractive force between two masses, and then we're also going to use superposition and point charges. For our preview, we end up getting a final charge of tape of 5.603 times 10 to the negative 9 Coulomb. So our assumptions, the first one is that the net y component of the force from tape B equals 0. So the momentum of tape B does not change, so therefore we can assume this. 2. Each U-tape has the same net charge. Each piece are the same length and width and were charged in the same manner with the same amount of force applied, so therefore we can assume that they have the net charge. We can also treat each tape as point charges with all the charges concentrated in the center of the tape. Additionally, we can neglect air resistance on the moving object. So for the experiment, our system is tape B, and then the surroundings are tape A plus everything around tape B. For our initial conditions, the length of tape was 0.2 meters, the width of tape was 0.0254 meters, and the mass of tape is 0.0002 kilograms. Additionally, gravitational acceleration is equal to 9.8 meters per second squared. So in our experiment, we take tape B, treat it like a point charge, and it floats above tape A, which is another point charge, and additionally both of them are charged tapes. Then we're going to measure the distance d between the two pieces for our calculation. So we do some calculations. First, we're going to do the magnitude of gravitational force on tape B, which is equal to mass times gravitational acceleration. So our mass from before was 0.0002 kilograms times 9.8 is going to equal 1.96 times 10 to the negative 3 newtons. Then our measured separation distance at which B floats is d equals 0.012 meters. Using these, we're going to determine the charge on tape B. So because the sum of forces on B equals 0, the electric force of tape B is equal to negative 1.96 times 10 to the negative 3, or equal and opposite to the gravitational force. We're going to plug this into Coulomb's law so that we can solve for the charge of tape B. And then we get 5.6 times 10 to the negative 9 Coulomb. The number of electrons on tape B is going to be equal to the charge of tape B divided by the charge of one electron. We're going to end up getting 3.491 times 10 to the 10 electrons. The number of atoms on the tape surface is equal to the surface area of the tape, which is length times width, divided by the area of an atom, which is the length of one atom squared. We're going to get 5.101 times 10 to the 17 atoms. Then the ratio of number of excess electrons to the number of atoms on the tape surface is the number of excess electrons divided by the number of atoms, and then we're going to get 6.968 times 10 to the negative 8. So for our coding, we're going to use what we wrote for calculating the electric field produced by a point charge from Lab 0, and then I wrote a code in order to produce a computational model of two charged tapes exerting an electric force on each other and experiencing gravitational force. This is going to be used to estimate the amount of charge on each tape, or in our case tape B, which is our system. So once you run this code, the charge on tape B ends up being 5.60286 times 10 to the negative 9. Some possible errors are that the tape is not an actual point charge, and treating them as so could skew answers. Additionally, the tape could have unequal charges in reality, which could also change our answers. So the fundamental physics principle would remain the same if the electrons had positive charge and protons had negative charge, because like charges will still repel and opposite charges will still attract. Therefore, our results would be the same. It's important to handle the charged tapes as little as possible because it would affect the charge of the tape, possibly neutralizing them and messing up the experiment. In conclusion, in this experiment, we use experimentation, calculations, and coding to approximate the excess charge on a piece of charge tape. The end result was 5.603 times 10 to the negative 9 coulomb. Thank you.